recording this, so we're live again. My apologies, there was an interruption again. My internet connection, stopped working. I think it's working right now. It is. So let me know if you're having any troubles hearing me or seeing. I'm going to, again, per my promise, I'm going to connect to Desmos. So somehow it's a good thing that we didn't start the problem quickly. So there we go, that's Desmos. Now I'm just gonna remind everybody we're looking at problem 22. So I'm gonna write myself a note here in case this collapses. At least this one saves, the Zoom doesn't. So there we go. So this is problem 22 from section 4.2. All right, so this is problem 22 from section 4.2, and the problem says this function f of x equals, and my function is going to be x squared minus 4x plus 2. But I don't want the entire function, but rather I want a part of it, and that part is from what is it, from 1 to 4. So what is 1 to 4? Okay, so I want this thing. Okay, so let's say 1 less than or equal to x less than or equal to 4 of this particular function, x squared minus 4x plus 2. Okay, this is the function that I'm looking at. And let's see what happens with the integral. Can we actually calculate this particular integral? So now this one here, folks, is quite an interesting question. One second. So what does it say here? Okay, form of a definition. Oh, okay, okay. So so it says here to use the definition. So all right, folks. So so we're gonna work a little bit on this particular function. Wasn't smart of me starting with this particular one, because this is going to be a little bit of work to actually get it. Okay, so oh, you know what? I wasn't looking at the right problem. Sorry, folks. I mean, problem. Okay, so there's two issues here. I wanted to do problem 24, not 22. So now I realize I marked it wrong in my my notes. So so folks, I'm gonna change to problem 24. And problem 24 is not that one, rather this one. So it's going to be, just make sure that everything is okay here, because I get all sorts of strange signals from the connection here. So so folks, if you don't hear me, do let me know. So over here we get 0, not 1. Okay, there's 2, 0 less than or equal to x less than or equal to 2. And the function is not this, but rather 2x minus x cubed. All right, so this particular function. Now, this particular function, as you can see, it's not something that you could speculate on, but it's easier to calculate. The calculation is easier than the one I did earlier, For the following reasons, we have to deal only with 2x, which is relatively easy, and then we have to deal with x cubed. So here's what I'm gonna do. I'm gonna say this. I'm gonna now, in order to do this particular function, we have to discuss about some properties, and I think I'm gonna do those properties first, and then I'll approach this problem. I'll show you how that is done. So this is gonna go the following way. So the idea here is to break down these functions, and for one of them calculate the integral of x cubed, and for the other one calculate the integral of 2x. So before we do this type of problem, I sort of jumped the gun here a little bit. All right, let's this was that interruption was not very good. So folks, okay, all right. So okay, there we go. Now we have a blank piece of whiteboard here. All right, so at least that is a good outcome. So so folks, some properties of definite integrals. Before we get to do further calculations, because without these we will struggle to do that particular type of problem. So the first thing that we need to keep in mind here, so if f is greater than or equal to 0, then that tells me that the integral from a to b of f of x dx is greater than or equal to 0. That doesn't say anything unusual. It says that if I'm over here and if I calculate again the signed area, that's going to have a positive sign, which we all already know. So we already discussed that. All right, that will be property A. Property B over here would be if, property, let's say property 1 and 2 or something like that. Mixing up a notation now. Property 1. Property 2 would be the following. So we'll say if f is greater than or equal to g, then the integral of a to b from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. Why would that be true? Well, it's very easy to see that, folks. If f is greater than or equal to g, it means that the graph of f and the graph of g are in this kind of position where the graph of f is here, is higher than the graph of g. All right. When we calculate the area, of course, this area over here will be lower than the area under the graph of f. So that is the case, and that takes care of the problem. Now, I'm not going to go into the details, but you could simply subtract, for example, and then see that that's the case, even when I have negative areas over here. Property 3, which is very interesting, says that if you do the, so I'm going to do this before I do the next one. If you do the integral from a to b of f plus g, or f minus g for that matter, dx, f plus g of x dx, you will get the integral from a to b of f of x dx plus the integral from a to b of g of x dx. So that is telling us something interesting. If we add two functions, folks, then the areas under their graphs add up, which is not unusual. So that can be easily seen when you have constant functions. So let's say one is the constant function f of x equals 3, and the other one is a constant function f of x equals 4. So the area under the first is, there we go. So you got the first one, f of x equals 3. Well, the area here is the area of this rectangle. F of x equals 4. You can move it up and you can say, you know what, I can add 3 plus 4 is 7, and the area under that will be equal to this one. This is a shift going up. But then this is f plus g. One of them is 3, the other one is 4, so the sum is 7, and the total area is the sum of the two. The same goes if you put a minus sign here. It's a little bit of work, really not too much, but a little more work, and that tells you that if you do things like that, so when you do integral from a to b of f minus g, you subtract the two integrals. So these are the properties. Finally, since we started with these properties, let me do one that is very useful for you, especially those of you who will do probability at some point. And this is called this has a name. It's called the average theorem. If you want, there's going to be a mean value theorem coming up. But before we do that, let's just notice this: if the values of f are between two constants, little lowercase m and capital M. So these are constants. And this is a constant. Constant and constant. All right, if these two are like that, then the conclusion here is that the integral of a to b, I'm sorry, so let me write it this way, folks. So we can say then, and I can say here, lowercase m is less than or equal, and you'll see something interesting here, 1 over b minus a, the integral from a to b of f of x dx is less than or equal to uppercase m. What does that say in practice, and how does this formula even come about? Folks, if you multiply both sides of this really tells you that b minus a m multiplied by b minus a is less than or equal to the integral of from a to b of f of x dx is less than or equal to b minus a, let me write it that way uniformly, b minus a times uppercase m. What does that mean? It really tells me graphically that if my function f is something like this and lowercase m is here and uppercase m is over here, so then if I calculate the integral from a to b, which I'm going to represent now with red, that will be the integral from a to b, folks. A and b are over here of f of x dx. Well, that is going to be greater than, and I'm going to represent with blue, greater than this area because m is strictly under the graph. But this area over here, the blue area is b minus a base times height, b minus a times lowercase m. And so the integral is also that area is less than or equal, and I'm going to color with pink here with this the big area, which is the big area being b minus a times uppercase m. So so the integral that I represented here with red is so this one here, folks, that I represented with red is actually, so the red thing is the integral from a to b of f of x dx. So you see that that integral is squeezed between these two values, and that's why the inequality, when you divide out by b minus a, you get this thing here. Now, what does that say in practice? In practice, it says that when you calculate the area and you divide out by this thing, by the length of the interval from a to b, well, what that says to me says that you're averaging all the thin slices that are possible here, because the area would be essentially one of these thin slices times the length, right? That would be kind of like, if you think of it, almost like a rectangle. So, so what we're saying here, we're saying that the average value of f from a to b is actually at least lowercase m and at most the uppercase m, which is not unusual because all the values of f are between lowercase and uppercase m. So the average value, this integral here, this is called the average value. of f. And that is going to be something that you will learn again, you will review in probability. So when you do probability and statistics, that's probably going to be one of the things, one of the things that you will learn there for sure, folks. Not probably, for sure. All right. So I'm not going to continue any further. Again, we're gonna get back and we'll do problems like those that I just said, and a few more problems like those coming up. So in the next lesson, we are going to discuss about the fundamental theorem of calculus. All right, folks, thanks for coming here. So be here Friday because we discuss the fundamental theorem of calculus. I apologize for the interruption. It wasn't something planned. It's just